Hello everyone, welcome back. Today we're going to talk about ray tracing in geometric optics for curved mirrors and for thin lenses, and then we'll go over some of the problems on the first problem of the day sheet. So here we have, starting off, we have a curved mirror, concave mirror here. And then, of course, for the concave mirror, there's the focal point and then the radius of curvature. So the radius of curvature, of course, is if we extended the mirror to a full circle, and then that would be our radius of that circle. And then the focal point is where light is being focused at if it's entering the mirror parallel. And for ray tracing, we're going to follow these rules that are over here on the slides, and you have these different pictures for how rays can enter. So one is entering parallel to the normal axis or the middle axis of the lens, and if it enters in parallel, it reflects through the focal point. And then, of course, rays that enter or pass through the focal point will be reflected out parallel. And then you can have 3 is striking the center, and that's going to reflect symmetrically about the center axis of the mirror. And then, of course, any ray that goes through the center of curvature hits the mirror at a 90 degree and just bounces right back through that point. And so these are the rules that we can use to do ray tracing to answer questions. So the first thing we're going to do is place an object. So let's go ahead and place an object. So here I have an object. So this is my object O. And when you're going to be doing this on quizzes or exams, it'll be very beneficial if you have a transparent straight edge or a ruler. So make sure you you get one of those from the bookstore or something, and bring those with you, your ruler, your straight edge, to the exam or quizzes. Preferably a transparent one, or as transparent as possible, so you can lay it on your sheet and see everything and draw nice straight lines. I have the benefit of my software here that'll draw the straight lines for me automatically. But anyway, so the question is I want to know about the image that is being formed by this object here. And to answer that question, we're going to use ray tracing, and we're going to use the rules. So the first rule I want to apply here is always a good one, is the first one, which just says that parallel light striking the mirror has to go through the focal point. So let me switch colors here real quick, and we can use green to depict the light. So parallel light, so if I have a ray coming in that's parallel to the mirror, now that light ray should reflect through the focal point of the mirror right here. Okay, so let's draw that. Okay, so light entering parallel from the image, from the object, is reflecting through the focal point. And then we can use the second one over here. Conversely, any ray that passes through the focal point reflects parallel to the axis. So you see this is going through the focal point and then reflects parallel through the axis. So we'll start that one. Again, over here, move that through the focal point. Okay, and so this one should reflect parallel out, and we see where do they intersect. So my two intersections, of course, is where the image is going to be formed. So this is telling me that my image here, let me use a different, let's use black. So my image here is in between the center of curvature and the focal point, and it is smaller, right? So it's decreased, however much magnification is being created by this scenario. Very good. So that's the example where what we've done here is we've placed the object away from the mirror past the center of curvature. So equivalently, we could have placed the object let's place the object right here. In between the point of curvature and the focal point of the mirror. And all we're going to do is follow the same rules. So I'm going to draw, let me switch colors again. Light that's parallel to the axis should reflect through the focal point. Okay, and then light that goes through the focal point should reflect out parallel. And so that gives us an image here. The image is now behind the object, or to the left of the object. It's enlarged. A few things we can note here. First of all, the object is pointing upwards, and in this case the resulting image is pointing downwards. It's magnified, it's larger than the object, and the important thing here is that it's a real image. Why is it a real image? Because if you follow the light is actually passing through the image. And we could place a screen here. We could place a screen right here and actually get a depiction of the image that you could see with your eyes or whatnot. So those are some important concepts. Let's do one more scenario where now we place the image in between the mirror. Now we've placed the object in between the mirror and the focal point. This scenario is a little bit trickier, but we'll still follow the same rules. So the first one I want to do is draw the one parallel. So when light moves parallel to the mirror, okay, now that should reflect through the focal point, like so. And then light that goes through the focal point and hits this point here, so from here to here, I want to draw light going through that point and hits the mirror. That should reflect parallel out. And you see over here that the two beams of light that are moving are not going to intersect. One is parallel to the center axis and the other one is moving away, so they're diverging away from each other. This is interesting. So the question here that you might ask is there an image? There is an image, but if you looked at where the light is traveling, the light will never pass through that image. So already we should conclude that the image is a virtual one. How can we construct the image? Let me use a different color. We can construct the image by completing these beams of light to the other side. So let's do that, and we'll use black for that color. So we'll complete this image. And so these are virtual lines of light because light is actually not moving through the mirror. And then we see we get the intersection point over here, and we get an upright image. So this image is magnified, it's upright, but it's virtual. And it's virtual because it's behind the mirror, right? So it lives in, if you want, like mirror land or something, behind the mirror. And so this is exactly the procedure that you would follow to reproduce these scenarios on this table, and this table is taken from your book. So the scenario on the right on the board is right here. You see the image, the object is between the focal point and the mirror, and we get a virtual, upright, enlarged image. Okay, we did this one where we had an inverted image, enlarged, and real, and then we also did, well, we could do this scenario. We did this one the other way, but let's redo that one just to get an idea and some practice. So here we, in this example, well, the example we did, let's just redo it again, was we had an object that's in between the center of curvature and the focal length, and let's redraw this. So we have light coming in parallel. Now that should reflect through the focal point. Okay. And then light going through the focal point, and that should reflect out parallel. And we get the image here. It's enlarged, but inverted. And so what the book is doing is it's starting with an inverted image, which then gives you an upright, I'm sorry, we're down here. This is the scenario I'm drawing. Apologize, I got the O and the I confused. But what I was saying, we could, if you had started with an inverted object, you would get an upright image. And so we just reproduced this scenario here. So now we can proceed and move on to from mirrors to lenses. And so lenses are going to follow. Let's look at the modifications we have to make. Lenses will follow the exact same rules. So light that goes parallel to the center of axis doesn't reflect, but instead refracts. So a lens will let the light move through. So let's look at the case 1. So 1, and so let's put an object over here, just for as an example. And so light, and let's use green again for light. So light that is moving parallel to the center of axis, and of course this is your center of axis, which is normal to the lens. and over here, light moved parallel, reflected through the focal point. For lens, it refracts. We say it doesn't reflect, it refracts through the focal point. So that's your modification for 1. So what we can do is label. So this would be 1. 2, if you hit the center of the mirror or the center of the lens, what happens? So let's do one that hits the center. What happens here in this case is we don't, so here it would reflect symmetrically about the center of axis. For the lens, it moves through the lens undeflected. Nothing happens. So that's the modification, and we already can see now where our image would be forming would be over here. And so that would be your image forming. In this case, it would form in between the focal point and twice the focal point, and it's inverted and smaller. Okay, so that and then this would be actually, I'm sorry, what I drew here was 3, so this is 3. See, any ray that strikes the center of the mirror reflects symmetrically about the mirror. So 3, any ray that goes through the center of the lens is undeflected. That's all that means. And now what we can do now is move through. Now let's do what was 2, which is moving through the focal point. Oh, that was 2. Right. So we can actually refract. So if I have light coming from the object through the focal point, that should refract through the lens parallel. And again, you see where the image is forming over here. So that should refract parallel, and we don't really need to worry about 4 because we're not in a mirror, we're using a lens. But 4 would basically mean that you would have to replace C with 2F, but that really that's not very applicable for lenses. So all you need to worry about for lenses is 1, 2, and 3, which we see here. So we could start asking questions using our lenses, and then we can do the same thing as we did up here, which is where we placed the object in a certain location and looked at where the image was forming. What was the image, real, inverted? In this example here, we have an inverted. The image is inverted. It's real because all the light is passing through the image, and it's decreased, obviously. So these are some examples on how we can use ray tracing to analyze our problems or questions in geometric optics. So here's one of the problem of the day sheets that's posted on Brightspace for chapter 21. And here's already an example. So in this example, we have problem 1, a convex lens. And so just to keep things straight, concave, oh, that's for mirrors. Here's for lenses. So a convex lens is the type of lens, or the example that we had up here. Concave lens would be, or diverging lens would be that type of an example there. And so here the question is a convex lens, so this type of lens has focal length f. If an object is located extremely far from the lens at infinity, the image formed is located what distance from the lens? Okay, this is a good question, and actually we have the right slide here on the left up, so we have to use a thin lens equation right here, which says we have 1 over s plus 1 over s prime equals 1 over f. And looking up here, s is always the distance that the object makes, and so this is the object, makes to the lens, and then over here, this would be S prime, the distance the image has from the lens, and then of course the focal length. And the question is we're going to place an object, so we want to place an object really far from the lens. That means that S over here is essentially at infinite meters away from the lens. What happens to this term now? Okay, and so you're looking at S goes to infinity, and let's rewrite that as, so we're looking at the limit as S goes to infinity of 1 over S, and that should give us 0, essentially. Why is that 0? That's just reflecting the fact that we are dividing out a really large number, and you can see that if we pull up our Mathematica, our calculator, and we bring this into frame, enlarge it a bit. Okay. So, and we can do 1 over S, and then S to infinity, and you see that gives you 0, because you're just dividing 1 by a really large number, and that gives you undefined, not undefined, essentially 0. Okay. So what that tells us then is that if this term is vanishing as S goes to infinity, we're left with a simplified version of the equation, which is 1 over S prime equals 1 over F, and then you can invert that to give you S prime equals F. So it would be located, the image should be located at F right here. Okay, problem 2, as you walk away from a vertical plane mirror, your image in the mirror is always the same height. May or may not decrease in height depending on whether the observer's where the observer's position is always a real image. No matter how far you are from the mirror, changes from being a virtual image to a real image as you pass the focal point, decreases in height. Interesting. So first of all, it's a plane, a vertical mirror, so there's actually no focal point. The focal point only occurs when you have curvature on your mirror right here. So this one is already, we can already rule that one out. Okay, is always a real image. C we should rule out as well. Why? Because if we have a plane image, a mirror, so this is your mirror, okay, and you have an object over on this side, and now we're sending light through. If that light is exactly perpendicular to the mirror, it's just going to reflect back, but that means that the image will be inside the mirror on this side. Okay, so if the image is inside the mirror, and it doesn't matter, well, let me draw this one like this, right there. So the image is on the other side of the mirror, or mirror land, on this side here of the mirror, which is virtual. So it's always going to be a virtual image. So C is not applicable here. may or may not decrease in height depending on whether the observer is positioned or where the observer is positioned. So here we have B and E are kind of the similar questions, but we should eliminate these as well, and then of course giving A the right answer. But why does the height not decrease or increase? Well, if you look here, we don't care about how far away the object is. This light is moving always at the same height, which is the height of the object, and parallel to each other, which means the image is always going to form on this side at the same height. So no matter how far away the object is from a plane mirror, the image is always the same height, and it's actually the same height as the object. Okay, which statements are true about a virtual image? There may be more than one correct choice. Its location can be calculated, but it cannot be viewed directly by your eye without using auxiliary lenses. Well, looking at problem 2, we know this is wrong, because everybody can stand in front of a plane mirror and see their reflection in the mirror. It cannot be photographed. Well, that's wrong again from here, because we've all taken selfies by looking in the mirror, and then you always see the picture on the internet, and you know the person took the picture in the mirror because you see their cell phone as they're holding it up and taking the picture. Cannot be viewed on the screen. Now this is true, and why? If we look at our ray tracing diagrams up here, or actually let's look at the one on the table. So in this case here, where the object is in between the focal length and the mirror, you see that the image is actually formed behind the mirror where light does not pass through. So if we placed a screen right here, there's no light hitting it from the object. So you actually cannot view a virtual image on a screen. So this one is correct. Okay, a plane mirror always forms a virtual image. That is correct. Just again, refer back to this example. You're always going to form a reflection in a plane mirror that's in the mirror world. A concave lens always forms a virtual image. A concave lens, and that is true. If you look at the table from the book, it doesn't matter where I place the object. By nature of the light refracting through a concave mirror is always going to diverge, which means the image is always going to form in front of the lens or wherever light cannot see it or cannot pass through it. So this is always a given, and it's stated just one example in your table in your book, and so this is true too. So we can highlight them with a different color. So these are the correct answers. Okay, so let's move on to problem 4. A convex lens has a focal length f. An object is placed at a distance between f and 2f on a line perpendicular to the center of the lens. The image formed is located at what distance from the lens? Okay, and then of course there are choices A, B, and C. 2f between f and 2f, and C is f, and I put in a blank space so I could do work, but it continues on the next page. D and E are over here. So between the lens and f, and farther than 2f. So let's use this blank space to do this. Let me add another picture of the lens here so we can do the work. And let's make it a little bigger. Good. So let's look at the object. So a convex lens, this is a convex lens, has focal length f. An object is placed at a distance between f and 2f. So we're placing an object right here. The image formed is located at what distance from the lens? This is a perfect example or problem where we can use ray tracing. And I want to use ray tracing, and I want to use the first two ray examples. So one, I'm going to have send parallel light from the object to the lens. That should refract through the focal point. Okay, and then I can send light from the object through the focal point. Oh, my lens is not big enough, but we get the point. If it, imagine lens was big enough, but the if I send it through the focal point, it should refract parallel oops, kind of messed that one up. Should refract parallel out, and we get our image formed over here. Now the image is enlarged, inverted compared to the object, but more importantly, it is located further away from 2f. So it is located at I'm sorry, that was the wrong symbol. Bigger than the 2f distance. So that would leave us with the correct answer is E, farther than 2f away from the lens. And again, just imagine the lens extended. If you want, what we could do is make our object a little smaller, and so it'll actually refract through the lens. So let's make it about this height. Good. And let's use green again for the light. So I have parallel light, and that will move through the focal point. And then I have light that goes through the focal point. And now we're actually hitting the lens. Very good. And we see we have our image formed over here, I, and again, we see we are greater than 2f away. And so again, that's E. Okay, next problem. Problem 5. A concave spherical mirror with a radius of 2 centimeters creates a real image 30 centimeters from the mirror. How far is the object from the mirror? Oh, that's interesting. To do this problem, I'm going to look at the table from the book on the slides. And so we have a concave mirror. So I have 3 concave mirror examples where the object is away from the center of curvature, in between C and F, and in between the mirror and F. And then this is a convex mirror. This one's not applicable because it says it's a concave mirror. It says that it's a real image. Okay, so that means that this scenario is not applicable. So this one forms a virtual image. So that means I'm over here. And these two, one of these two. Okay. And a concave spherical mirror with a radius of 20 centimeters creates a real image from the mirror. How far is the object from the mirror? Okay, and the spherical mirror has a radius of 20 centimeters. So let's look at that. So R here is 20 centimeters. And so if R is 20 centimeters, that means F is going to be the magnitude of R over 2, which is 10 centimeters. Or what I should say, actually, if we look at the notes or the slides, it's the opposite. The magnitude of the focal point is R over 2, which is 10 centimeters. Now, I don't know anything else, and that was up here on the ray tracing slide right here. So here's that equation. Let's go back to the table. Here we go. So if the radius of the focal point is 10 centimeters and it creates a real image at 30 centimeters, that means, again, we're either at these two positions here. And we want to know now 20 centimeters, so we know S prime is 30 centimeters. S we don't know. And I think that's it, right? How far is the object from the mirror? So we have 1 over S plus 1 over S prime equals 1 over F. And so now we can solve for S. And let's use our Mathematica for that. So we have 1 over S plus 1 plus 1 over, and now we have S prime, which is 30 centimeters, and that equals 1 over 10 centimeters, and then we can solve for S. And I made a syntax error, and we get 15 centimeters. So of course you'll need to show all the correct steps in algebra on your quizzes and exams. And that leaves us with C. Okay. Okay, next problem. Problem 6. In the figure, the image is viewed on a screen that is 13.5 millimeters tall. What is the focal length of the lens? Okay, so this is a lens. Let's go to the table for lenses. So here we are for the lenses. And first of all, we should notice, look at the object. The object here is upright, and the object's original height is 9.7, and it's being magnified. So look at the cases here where you're magnifying an object with a convex lens. And of course this is a convex lens. So we have 3 rows here for convex lenses, and we have 2 examples where it's being magnified. We have here it's magnified and here it's magnified. We don't know, we want to know the focal length of our length. So we know S is 35.0 centimeters. And we know we can call this H. So H is 9.7 millimeters, and H prime is 13.5 millimeters. And I'm leaving some space here because I might I'm not sure yet, but I might think I need to put a minus sign or a plus sign there, because if you look, if it's inverted and magnified, I need to put a minus sign here. If it's upright and magnified, then I need to put a plus sign there. So which situation do I have? And it doesn't seem that we have much more information numerically, but in the statement of the problem, it says problem 6, in the figure, the image is viewed on a screen. The image is viewed on a screen. So if you look up here, where was it? Here it was. Problem 3. Which statements are true about a virtual image? It cannot be viewed on a screen. So this scenario, in this scenario, it is being viewed on a screen, so it can't be virtual. And you see here, this is the virtual case where I have magnification upright. But if it's not virtual, it's real, that eliminates the only possibility for it to be right here, which means that it's inverted. So if it's inverted, H prime is minus. And then we have the magnification. So this tells me here that H should be equal M, H prime should equal the magnification times H. And this gives me a new equation that the magnification is H prime over H. And then looking at the slide, I know that that's minus S prime over S. So this gives me a new equation, H prime over H equals minus S prime over S. So now I have the thin lens equation, 1 over S plus 1 over S prime equals 1 over F. And F is what we're looking for. So I have F is going to equal 1 over S plus 1 over S prime to the negative 1. And then here, looking at this equation here, I know that S prime is going to equal minus S H prime over H. So I have F should equal 1 over S plus 1 over a minus S H prime over H all to the negative 1. And we can now plug in our numbers. So I have 1 over 35, and that'll be in centimeters, plus 1 over, and I'll have minus 35 centimeters, and then here I'll have H prime, which is minus 13.5 over 9.7, and the millimeters cancel. And so my final thoughts for this, we'll go to Mathematica. And so I'm doing all this to the negative 1, and I have 1 over 35 plus 1 over, and then what happens here, I just have two negatives which give me a positive. So I have 35 times, and then I have 13.5 over 9.7, and we do this out, and we get a focal length of 20.4 centimeters. And we could have put the centimeters in here, and Mathematica would give us the right units at the end as well. Very good. Moving on. So problem 7, an object is placed 10 centimeters from a convex lens of focal length 20 centimeters. What is the lateral magnification of the object? Okay. So an object is placed, let's write some things down. So an object is placed 10 centimeters from a convex lens. The focal length is 20 centimeters. What is the lateral magnification of the object? Which is minus s prime over s. And that is the question. And this is again a situation with lenses. I also don't know s prime. So the first thing to do, I do know the thin lens equation. So the first thing would be is to find s prime and then find the magnification from that. First of all, I noticed that the if you look right here, the object is placed between the focal point and the lens. Between the focal point and the lens, which is right here. So if we place an object between the focal point and the lens, that means that the image is going to be virtual. Okay, and if you look at the way we've defined S, so here, of course, this was S here, and then right here is S prime, and we've always called this positive. Positive S prime, and this would be positive S. But now we got to be able to distinguish the fact that the image is formed to the left of the lens, even though we usually say denote it positive to the right. Okay. So in other words, if let's add so if we add the object here, and then we can look at light. So of course light passing the center is undeflected, and light hitting, or let's go backwards. Let's do light going through the focal point is, or actually let's follow the table. We have light hitting parallel the lens, reflects through the focal point. And then let's go with green. So that means we would have an image back here, and then as best as I can make it over here. Good. So that means we have the image forming over here. So this is S, but now we have S prime, and so this should be negative, whereas this is still positive. And we're just saying that it's negative because when it forms, when the image forms on the right side of the mirror, then we call it positive. Now the image is forming on the left side of the mirror, so we gotta reflect that in our choice of sign. So S prime should be negative here. So S prime, we don't know, and we know it should be negative. So that's our only concern. So what is the lateral magnification of the object? That was the question. So the first thing we got to do is find S prime. So we have 1 over S plus 1 over S prime equals 1 over F. So let's plug this in. So we have 1 over S is 10 centimeters plus 1 over S prime equals 1 over 20 centimeters. So S prime. And we can go back over here. Let's call, so we're looking for S prime, so I'll call it SP. And S was 10 centimeters. And the focal length was 20. And it's empty because I forgot to say solve for S prime. And we get S prime is minus 20 centimeters, which corroborates our picture up here, and of course the table. The table here. So we're in this scenario, and the image is to the left of the lens, so it should have a negative S prime value. So now we're ready to compute magnification, which is minus S prime over S. So that's going to be minus 20 over 10. So that's just 2. And that's good. And if you look at the example here, it should be upright. So the magnification should be positive. It's enlarged, in fact, doubled. And everything worked out nicely. Okay, so this is the first video. We'll cover the other POD sheet for chapter 21 on a separate video.